Alright, so now that we've taken all of our two-dimensional vector theories and extended them so they work in three-dimensional space, it's time for us to cover some new concepts. And the first concept I'd like us to look at is the concept of the Cartesian vectors, and that's going to be the focus of this video. Now, those of you who are only just starting out with vectors and vector theory may feel that the concepts that we're covering in this video are a little bit abstract. They may seem a little bit strange. They're only going to be using theories that we've seen up until this point, but their use and their purpose may seem unclear at first. It may seem a little bit redundant why we're taking the approach that we are in this video for a way to represent vectors. If that is the case and that's how you're feeling as you're watching this video, I ask that you just bear with the video, watch through all the theories, sort of try to understand the theory and take it in, and hopefully through later videos and also other topics of discussion where I bring up some of the uses for these vectors towards the end of the video, hopefully that will allow you to see some of the power of representing vectors in this sort of alternative form than the form that we've been using so far. So again, it's only using theories we've seen up until this point, so there's nothing really complicated in the mathematics that we're using, but the theory itself, the concept itself, may seem a little bit abstract and it may seem a little bit redundant, but do just bear with it because hopefully everything will become clear, if not in this video, then certainly in later videos in this series. So the concept we're looking at is that of the Cartesian vectors. Well, we know we have our Cartesian space, and our 3D Cartesian space is defined by our three Cartesian axes. We have an x-axis, a y-axis, and a z-axis. So if I was to draw a set of three-dimensional Cartesian axes here on the whiteboard, we'd have an x-axis, a y-axis, and a z-axis, and of course we'd have our origin. Now, I'm not going to actually label the origin on this diagram, you'll see why in a second, just because otherwise that area of the diagram is going to get very cluttered, but we know of course we do have an origin that helps define our space along with our three axes. Now, what if I was to create three vectors in our Cartesian space? Now, these vectors are going to be very special vectors. They have a set name, and these names are known throughout pretty much every mathematical textbook. If they're referring to vectors with these names, they mean these specific, very special vectors. Now, they're very basic vectors and they're very simple concepts, but they are a special set of vectors. And these vectors are I, j, and k. So what's so special about these vectors? Well, the first thing that's special about them is that they are all unit vectors. Now, you notice I haven't actually written these as unit vectors. Again, that comes from the fact that it's kind of a special vector where if someone says I have a vector called I, they are pretty much always referring to this special vector that does have a length of 1, so they don't actually note it as being a unit vector. But it is a unit vector. All three of these are a unit vector, which means they all have a length of 1. But what else is special about that? We've seen unit vectors up until this point, and we haven't made a huge deal about them. I mean, they're going to be useful, but they're not that special to assign these three particular variable names to some unit vectors. The fact that they're unit vectors alone, surely that can't be the reason that we're doing this. Well, no, it's not. There's actually another property about these vectors that is very useful and very powerful, as we're going to see throughout later videos. And that's that each of these vectors runs in the direction of one of our Cartesian axes. So our I vector is going to run in the same direction as our x-axis. Our j vector is going to travel in the same direction as our y-axis. And our k vector is going to travel in the same direction as our z-axis. So we have x, y, z, and we have I, j, k. I is going to travel in the same direction as x, j in y, and k in z. So if we were to write these in terms of their Cartesian components, we know if they're unit vectors and they're travelling only in the direction of one of the axes, the I, if it's travelling in the direction of x and it's 1 unit long, is going to have the components 1 in x, 0 in y, and 0 in z. And it might look something like this. We might have a vector here, and this vector would be our vector I if this was 1 in our x-axis, so this would make this 2 in our x-axis, 3, and so on. So our vector I travels in the same direction as our x-axis, and it has a length of 1 unit. Likewise for j, if it's traveling in the direction of our y-axis and has a length of 1 unit, it's going to be 0 in x, 1 in y, and 0 in z. So j might look something like this. If this was 1 in y, this would be 2 in y, and so on. And k is a unit vector that travels in the direction of z. So it's going to be 0 in x, 0 in y, and 1 in z. So k would look something like that if this was 1 in z, this was 2 in z, and so on. So we've defined these three vectors. Now these three vectors, I, j, and k, are the Cartesian vectors, and they're called that because each one of them can be used to represent our Cartesian axes, if you will. I represents x, j represents y, and k represents z. So I, j, and k are our Cartesian vectors. But why might we want to have these three vectors that simply travel in the direction of x, y, and z? Well, we've seen some other theories that we can combine with these vectors. We've seen the scalar multiplication of a vector, and we've seen vector addition and subtraction. So let's combine scalar multiplication of a vector with our three Cartesian vectors and see why that might be useful to us. So to do that, I'm actually going to erase part of our diagram. So I'm going to erase part of the diagram just so that we have a little bit more space, so that hopefully this is as clear as possible, because I don't want things to be cluttered. Fantastic. Get rid of this as well. Much better. So we have a load of space now. So I'm going to pick on I, which we know is a unit vector that travels in the direction of x. So if I was to actually start I at the origin, now I isn't a position vector, it's just a normal vector, so the same with j and k, they're free to float around our Cartesian space. But if I was to pick a point to draw this from, and I drew it from the origin of our Cartesian space, we saw that I would travel in the direction of x, and we know that I has a length of 1. So we've seen that we can multiply a vector by a scalar value. For example, I could take the vector I and I could multiply it by a scalar. So I could say s multiplied by I. And when we do this, we know that what's actually going to happen, as I scroll down just for a second, so s times I, we're going to take our scalar and we're going to multiply it by that vector, which again, I is a unit vector that travels in the direction of x. So we have 1 in x, 0 in y, and 0 in z, which what we're going to get is a vector where we take s and multiply that by the x component to get our x component, so s times 1, s and multiply that by the y component to get our y component, which is s times 0, and s multiplied by the z component to get our z component, which again is s times 0. Which hopefully we can see that s times 1 is just s times 0 is 0, and s times 0 is 0. So if we take s times I, we're going to get a vector that has s as the x component, 0 as the y component, and 0 as the z component. So what this means is we can make any vector that travels in the direction of x or in the direction of negative x of any length, and the length of that vector will be specified by the scalar that we multiply I by. Now again, this may seem quite abstract, it may seem a little strange, just do bear with me, hopefully everything will start to fall into place as we piece these different elements together. So we're taking a vector, I, and we're multiplying it by a scalar, and that allows us to get any vector of any length in our direction of our x-axis or in the direction of our negative x-axis. If we repeated this process for j and for k, if I had some other scalar, so instead of s, let's say I used t, and I multiplied t by our j vector, which we know is 0, 1, 0, I'm going to get, and I'm going to skip out the middle stage here because it's quite obvious. We're going to get t times 0, which we know is 0. We're going to get t times 1, which we know is a value of t. And we're going to get t times 0, which is a value of 0. So whereas we had s times I, and it gives us a vector that just has s in our x component, when we take t times j, so this is equal to t times j, we get a vector that has just t in the y component. So if we were to multiply j by a scalar value, we're going to get some vector that travels in the same direction as our y-axis, or in the direction of our negative y-axis, that can be any length as dictated by that scalar value t. So whatever scalar value t we choose is going to become the y component of our vector. It's going to allow us to have a vector that travels in the same direction of y of any length. Hopefully it's logical that we can apply this to our k vector as well, our z-axis vector. So we could take another variable. We've used s, we've used t, so let's use u. And I'm going to multiply that by our k unit vector. So 0, 0, 1, which is our k. It travels in the direction of z. And hopefully it's obvious that that would become 0, 0, and u, which is equal to u times k. So we're taking our vector k, which travels in the direction of the z-axis, and by multiplying it by a scalar, we can change the length of k, we can invert the direction of k, and we can get any vector that travels in the positive or negative z-axis, and that can have any length. So what we've got is we've got the ability to create any vector that can travel in the x-axis, I'm sorry, that's the y-axis, in the x-axis or negative x-axis of any length by multiplying I by a scalar value. We've got the ability to create a vector that travels in the y-axis or negative y-axis of any length by multiplying j by a scalar value. And we've got the ability to create a vector that travels in the z-axis or negative z-axis of any length by multiplying k by a scalar value. But why might these vectors be useful to us? Why might it be useful to travel in x, travel in y, and travel in z? Well, to demonstrate that, I'm going to scroll down and draw a new set of axes. Oh, as Photoshop goes a bit crazy. So I'm going to draw a new set of axes. There we go. So again, we have x, we have y, and we have z. And let's say I had some arbitrary vector. Now, it's going to be a little hard because we're drawing this in 3D, but if I had some arbitrary vector that started at this point and travels up to this point, so here is our vector. Now, this vector is going to travel a certain distance in x, a certain distance in y, and a certain distance in z. Just like any vector, we know it travels a certain distance in x, y, and z as given by the components of that vector. But why is this of significance? Why is this important to us? Well, we also know that when we add vectors together, we can create a vector chain where if we started with a vector, for example, and added another vector to it such that it touches the end of the first vector, and then we carry on from that point in the direction of the second vector, and then added another vector to that, we know the resultant vector is equal to the vector that travels from the start to the end of that vector chain. So if we have some vector that travels a certain distance in x, a certain distance in y, and a certain distance in z, and we know that by scaling our I, j, and k vectors, we can travel a certain distance in x, a certain distance in y, and a certain distance in z, what that means is surely if we add together the scaled version of I with the scaled version of j with the scaled version of k, we can represent this arbitrary vector. And indeed we can, because we'd scale I to travel a certain distance in x. For example, we'd create a vector that looks like this, and this would be our s times I. And then we'd add onto that our scaled version of j so that we can travel in a certain distance in y. For example, let's say we travel like so. So we take our t times j, And I've mentioned that I is a unit vector, but we don't actually note it as being a unit vector, so I should change that to just being a vector. It's perfectly valid to have it written as a unit vector, it's just that's not the convention when writing I, j, and k. So we've travelled a certain distance in x, a certain distance in y, and then we can travel a certain distance in z, which we know was given by u times k. So by scaling the three Cartesian vectors, by multiplying them by these scalar values, if we then add those together, we can create any vector in our 3D Cartesian space. But what are we going to notice about the three scalar values and how that relates to our vector? Well, if this is our vector v, we know v, being a 3D Cartesian vector, has an x component, a y component, and a z component. And the x component tells us how far do we travel in x. Well, notice to travel that distance in x, we had to use s times I. And we said that s was going to affect how far we travelled in x. It was going to explicitly affect how far we travel in x, since I just represents one unit in the positive direction. So logically, if we travel x units in x, and here we have to travel s units in x, and s is equal to x, we could actually rewrite our vector multiplication here to take the x component of our vector v and write x times I. So we take this component, we multiply that by our Cartesian vector I, and that's going to tell us how far we need to travel in the x direction. Likewise, our vector v travels y units in the y direction. So we know that to travel y units in the y direction, we multiplied our Cartesian vector j by our scalar value t. Well, t is telling us how far we travel in the y direction, and it has to be the same as how far our vector v is travelling in the y direction. So we can replace this with y. So we take the y component of our vector v, multiply that by our j Cartesian vector, and that's going to tell us how far we travel in y. Finally, we needed to travel in z. How far did we need to travel in z from the start to the end of our vector? We needed to travel z units in z. So we can take this u and we can replace that with the z component of our vector v. So if we use the z component of our vector v and multiply that by our k Cartesian vector, it's going to give us a vector that travels the same distance in z as our vector v does. But how do we get from the start of v to the end of v? We have to add each of these vectors together. We know if we start at the start of v, and that can be anywhere in Cartesian space, just as we discussed when we were adding vectors. Anywhere in Cartesian space, if we start at a point in Cartesian space and travelled from that point in the direction and length of v, we could also travel from that point along our x times I. Then once we've got to the end of that, we then need to travel in the direction of y times j, which means we need to add y times j to x times I. So we have x multiplied by I, and then we add to that y multiplied by j. And once we've got to the end of there, we then need to travel down z multiplied by k. So we need to add to that z multiplied by k. And we know this is equal to our vector v. We start at the same point, we end at the same point, therefore they're equal. So our vector v is equal to x times our Cartesian vector I plus y times our Cartesian vector j plus z times our Cartesian vector k. So I'm going to rewrite this. If we have a vector v which is equal to x, y, z, and we have a vector I which is equal to 1, 0, 0. Now I'm writing this in row form just to save space on the whiteboard. We know they are, when we're working with vectors, they are interchangeable. J is equal to 0, 1, 0, and K is equal to 0, 0, 1. We can write V is equal to xi plus yj plus z k. So we can write any vector as a combination of our three Cartesian vectors. So as we scroll right back up and refresh our memory of when we were creating these vectors, and it may have seemed a little unusual. Why are we creating these three vectors? Well, the reason we're creating these three vectors is by defining these three vectors, we're able to represent any other vector as a combination of these three vectors by multiplying I, adding that to a multiplied version of j, and adding that to a multiplied version of k. In other words, we scale I, we scale j, we scale k, and we add those together, and that lets us represent any vector in our Cartesian space. Now that may still seem a little bit abstract and a little bit unusual, because you may be saying to yourself, well, we can represent any vector in our Cartesian space by using its x, y, and z components. Well, you're going to see in the next video, I believe, you're actually going to see why representing a vector in terms of I, j, and k can become very useful and very powerful for mathematical proofs, but there's actually a more overall theory here that, while we're not going to get into detail on it in this DVD, is actually incredibly useful. And that theory is that it allows us to think of our Cartesian coordinates here for our vector v as being multipliers of three vectors. So rather than thinking of our axes as such, our Cartesian axes, instead what we're thinking of is our three vectors. We're thinking of I, we're thinking of j, and we're thinking of k. Now we know that they relate to our Cartesian axes, but from that point we can think of the components of our vector as being three scales of each of those different vectors, and then we add those together and define a vector in our 3D space. Now this becomes useful when you start defining your own coordinate systems. For example, if you have an object that's translated to some position in the 3D world and it's rotated and maybe scaled, it may have its own local coordinate system where it has its own set of axes. They don't match the Cartesian axes of our world space, but it does have its own set of axes. You could then represent any position in that world, any vector in that world, in terms of the local space of that object by taking a vector, and let's say instead of using x, y, and z, let's say we used x local, y local, and z local, taking those and multiplying each of these by the vectors that are the local vectors of that object. If we had some object, let's say we had an object and it had its own local vectors, we could represent a point in our world in terms of this space rather than our world space by using scale factors of these vectors. And that's very useful. Now again, it's far beyond the scope of this DVD. We're not actually going to be looking at defining custom coordinate systems in this DVD because it really is quite advanced. There's a lot to it, there's a lot that's involved. But I did want to cover I, j, and k here, both for the theories and proofs we're going to see later in this DVD, but more because it forms a basis of thinking about how we can represent positions and vectors in our 3D space in terms of three vectors. We can define our 3D space using three vectors, and there's actually some special properties about those vectors, but again, I'm getting way ahead of myself and way out of the scope of this video. But we can define our 3D space using three vectors, but those vectors don't actually have to align to x, y, and z. They could be in some other position and orientation in our 3D space, and as long as we know that, we can still represent any point in that space as multiples of those vectors. That's very useful to us because it's going to be a concept that can be built upon in more advanced theories that allow you to define local coordinate systems for objects. They allow you to transform back and forth between different coordinate systems, which is something we do a lot in both computer graphics, and it's also very powerful when you're using programming to solve problems to be able to change things about in different coordinate systems. And I, j, and k, though very simple, and it may seem like a redundant concept, these are actually the foundation, if you will, of those more advanced theories. So I really wanted to cover those here, so if you decide to look into these more advanced concepts on your own, you're going to have the foundation, hopefully have a solid understanding of that foundation. So once again, just to recap, we have three vectors. Each of these vectors are 1 unit in length. I travels in the same direction as our x-axis, j travels in the same direction as our y-axis, k travels in the same direction as our z-axis. That gives us these three vectors, and by using those three vectors and scaling them, as I scroll back down, there we go, and scaling them by three scalar values, we can create any vector in our 3D space, because we know that if we take the x component of that vector, the Cartesian x component of that vector, and multiply that by I, and add that to the y component of that vector multiplied by j, and add that to the z component of that vector multiplied by k, the result of that is going to give us the same vector. We're simply going to travel a certain distance in x, a certain distance in y, and a certain distance in z, which is all that our vector does in the first place. So hopefully everything in this video has made sense, and even if the power of it isn't still clear, hopefully the theory and the concepts are clear. Hopefully why we have these three vectors, the fact that they're unit vectors, and the fact that they're in the direction of the x, y, and z axes, and how we can use them to represent any vector. As long as that's clear, that's the most important part from this video. And there's really nothing to test here, short of asking you to write a vector in terms of I, j, and k, which is as simple as taking these components and placing them into that equation. So I'm really not going to test any of your knowledge here. I guess I'll just work through one example myself in case anything's still not 100% clear, but outside of that there's not going to be any questions set in this video. So if I was to bring up a new whiteboard, and I am going to quickly rewrite that if we have a vector v is equal to x, y, and z, then we know v is equal to x times I plus y times j plus z times k. Now if I had another vector a that was equal to 2, minus 5, and 7, say, then we could equally write a as equal to 2i minus 5j plus 7k, because we've taken the x value, 2, we've multiplied that by I, that's given us 2i, we've taken the y value, minus 5, multiplied that by j, that's given us minus 5j. If we add minus 5j, that's going to give us minus 5j. And then we've taken the z value, which is 7, multiplied that by k, and that's given us plus 7k. So it's really simple, but just in case you were wondering how our sort of generic version maps in terms of a real vector, that's how it would work. You just simply take these components and you use them as scalar multipliers of I, j, and k. And with that, that really is going to conclude everything that I wanted to cover in this video. Thanks a lot for watching, everyone.